AP Physics 1, 2016 free response. Question number 1. A wooden wheel of mass m consisting of a rim with spokes rolls down a ramp that makes an angle theta with the horizontal as shown above. The ramp exerts a force of static friction on the wheel so that the wheel rolls without slipping. First part of part A. On the diagram below, draw and label the forces, not components, that act on the wheel as it rolls down the ramp, which is indicated by the dashed line. To clearly indicate at which point on the wheel each force is exerted, draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. The length of the arrows need not indicate the relative magnitudes of the forces. Okay, so we need to draw a force diagram. First off, as always, we can start off with the force of gravity, starting from the center of mass and pointing downwards, even if the object is on an incline. Now, since the wheel is rolling due to friction, that must mean friction is at play. Now, since our wheel is rolling down the hill, that means our movement is going towards the right. So since friction opposes motion, friction would be towards the left. And since friction is at the point of contact between the object and the surface, that means friction would look like this. Now, since we're in contact with the surface, that also must mean there's a normal force, which is perpendicular to the surface at the contact point as well. That's why we can draw a normal force such as this. So that would be it for our forces. Now for the second part of part A. As the wheel rolls down the ramp, which force causes a change in the angular velocity of the wheel with respect to its center of mass? So here's our diagram from earlier. Now we want a force that would change the angular momentum. So we know the change in angular momentum has to be due to a torque. So torque is equal to R, which is the distance from the center of mass to the contact point of the force times the force itself. And the R vector and force vector have to be perpendicular. So here's the center of mass for reference. And the force and the center of mass to the force have to be perpendicular. So if we look at our forces, it's only frictional force. Here's our center of mass, and here's the contact point of the force. So if we imagine a line here, and we see frictional force here, we see that they form a 90-degree angle and are perpendicular. But if we try this with other ones, such as force of gravity, we see that the two are parallel, so there's no torque generated by the force of gravity. Now, if we look at the normal force as well, they are also parallel, so no torque is generated in this case as well. So thus, with our original answer, frictional force causes a change in angular velocity, since only friction exerts a torque. Part B. For this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static frictional force. Instead, the magnitude of the force of static friction exerted on the wheel is 40% of the magnitude of the force or force component directed opposite to the force of friction. Derive an expression for the linear acceleration of the wheel's center of mass in terms of m, theta, and physical constants as appropriate. So here's our force diagram for reference again. So we're looking at force. Since we're looking at forces and we want to find acceleration, let's start off with Newton's second law, where the net force is equal to mass times acceleration. So what is the net force? Well, we're looking at the object going down the ramp. So let's focus on this in this direction. So going down, we have the component of gravity, which is Fg sine theta. And opposing this in the opposite direction is the frictional force. So all this is equal to mass times acceleration. Now it says that frictional force is just 40% of the force opposite to it. So the force opposite to it is the component of gravity. So the force of friction would thus be 40% of that. So it'd be 0.4 Fg sine theta. So we can simplify this to say 0.6 Fg sine theta is equal to ma. Now let's solve for acceleration. First, we can expand Fg to be 0.6 mg sine theta, as force of gravity is equal to mg. Now we can divide mass on both sides to solve for a, which would be 0.6 g sine theta. Part C. In a second experiment on the same ramp, a block of ice, also with mass m, is released from rest at the same instant the wheel is released from rest, and from the same height. The block slides down with this ramp with negligible friction. Which object, if either, reaches the bottom of the ramp with the greatest speed? Briefly explain your answer reasoning in terms of forces. So let's first picture the block of ice. So this rectangle here would represent the block of ice. Now let's look at the forces on it. Of course, we'll have the force of gravity as well as the normal force since it's in contact with the surface. But there's no other forces as it says the block slides down with negligible friction. So we can say the block will have a greater final speed since there's no friction on the block. So since the force of friction exerts the same component force of gravity, which is Fg sine theta, the only force acting in that direction would be Fg sine theta. But in the wheel, the force of friction opposes Fg sine theta. So the overall force going down the ramp is less for the wheel compared to the block. So since the wheel has friction, it has a less net force going down the ramp, meaning it has less acceleration. Thus, the block will have a greater acceleration, so it will go down the ramp with a faster speed. Now for the second part of part C. Briefly explain your answer again, now reasoning in terms of energy. Let's focus on the energy portion now. Let's start with what we know. The wheel has friction, which causes it to spin. And spinning means angular velocity. Note that both start at the same height, so they have the same initial energy and gravitational potential. And both end up falling down the ramp. So let's look at the block first. The block's initial energy converts to translational kinetic energy since it's just sliding. Now let's look at the wheel. The wheel's energy converts to translational and rotational kinetic energy. In this sense, it's spinning, which means it has angular velocity and thus rotational kinetic energy. So all this means that it will have less transitional energy as some of the rotational energy has to be taken up, so less energy can be allocated to the translational portion. So in a paragraph form, we can say both the wheel and the block convert the same initial gravitational potential into kinetic energy, but the block's final energy is only translational kinetic. Sorry for the spelling error. Since the wheel spins, the wheel also has rotational kinetic energy, so less energy is translational kinetic. Thus, the block's greater final translational kinetic would mean the block has a greater final velocity. And this matches our previous answer in the first part of part C. Well, there you have it. That would conclude the first question of the 2016 free response. In the next video, we'll follow up with a second question.